Hello, everyone. What I want to do now is put the Riesz representation theorem proved last time to good use and talk about reproducing kernel Hilbert spaces and the connection between reproducing kernels and orthogonal projections. So remember what the Bergman space was, and particularly when p equals 2. We define this as all holomorphic functions on the unit disk where the following is finite. And I will stick a pi here. It makes things so much easier, as we'll see in a moment. This is just ordinary area integration over the disk. And this quantity, this has to be finite. And this quantity here is, of course, just the norm squared of my function here. And the inner product is just simply, like I said, I'll stick a pi here just because it makes things a lot nicer looking, really. Not any easier, but just nicer looking. Yeah, maybe I'll use W because I'm going to use Z in a moment. Right. Okay, so remember what we did a few videos ago when we talked about the Bergman space. We proved that so in one of the previous videos, we proved when p equals 2 that for any z in the unit disk and f in my Bergman space, the Cauchy-Schwarz inequality and the area mean value theorem give us that modulus of f of z is less than or equal to, we had a pi here, but that's going to get absorbed into the norm. So it's going to be 1 over 1 minus z times the norm of f. Actually, I think this should be a, no, that's fine. I think actually it might be a squared here. But yeah, so the idea, no, actually there is no squared. And yeah, it should actually be a pi here. 1 over pi, 1 minus modulus z times the L2 norm of f. So what does this tell me? This tells me that, let's say E for evaluation, Ez of f is just f of z. Then, well, this is very easily seen to be linear. There's really nothing to show there. So this says that Ez for fixed z in the unit disk, again, E is for evaluation, so it's like evaluation at z. This is in the dual space of the Bergman space. It is a bounded linear functional on the Bergman space for fixed z. Okay. Right. So there's certainly, I mean, as z approaches the boundary, well, this constant here blows up to infinity. So, you know, there's no uniformity among the operator norms as z varies around, you know, in the disk. But for each fixed z, Ez, by what I have exactly right here in blue, Ez is a bounded linear functional. So by the Riesz representation theorem, there exists an element depending on Z in my Bergman space where Ez, which is f of z, Ez of f, which is f of z, is given by inner product of f and this element kz, whatever it is, in my Bergman space. Let me move this down so I have more room. So let's kind of start to unravel. I mean, I guess if you've seen this in Kay's course, it's not really unraveling anything, you know, the whole plot of probably this whole lecture. But if you haven't, or if you forgot, that's probably even better. Right, so what is this going to be equal to? Well, we know what the inner product is. It's just 1 over pi times this integral here. Whatever this function is. So we want to answer the following question. Well, what is this? Literally, what is this function here? So the answer is actually basically a prelim problem. Not exactly. There's a little bit of, 510A detail to make this rigorous. But so if you go to January 2016 complex analysis prelim, you'll see the following prelim problem, which I'm going to use. The proof is really not bad. You follow the hint, and that is do power series expansion. Got to be a little careful to do uniform convergence of power series expansion. But so here I have a double integral, but you can really get rid of one of the integral signs. Right, and well, u is just a dummy variable, so it's just use w here. Okay, but yeah, this is saying as if f is bounded and holomorphic on the disk, then f of z is given by 1 over pi times this integral here. All right. So we can't just immediately use this to say we know what this reproducing kernel is, because functions in the Bergman space are not bounded, but we can do a very easy trick. All right. So I'll just write down exactly what I had a second ago. So if I have, let's say, big F, that's holomorphic on the unit disk. Let me make that a little neater. And it's bounded. Then for any z in the unit disk, we have the following. All right, so let's say little f is now in the Bergman space. So for some r between 0 and 1, we can kind of force f to be bounded in some sense by the following little trick. Let's say big F is just f of r z. Okay, so for any z whatsoever in the unit disk, I mean, I probably don't have to write this down, but so right, so this is going to be, rather, these two are equal. So this is less than r is less than 1. All right, so so that means that big F is certainly bounded on the unit disk. All we're really doing is looking at f of stuff that's bounded above by r, which is strictly less than 1. So certainly we're in a, I mean, yeah, let's doesn't even matter. It's less, let's say it's if it's less than r, it's less than or equal to r. So you know, RZ for any z in the unit disk sits in a compact subset of the unit disk. F is continuous on the unit disk, so F is bounded on, big F is bounded on the unit disk. Of course, that bound could possibly blow up as r goes to 1, but that's okay. We don't really care. All right, so let's just write this down. Yeah, sorry. That should be big F. I don't know why I wrote little f. So yeah, I'm not going to write big F, but what I'm going to write is just everything here, but replace big F with f of r z. So this is going to be equal to 1 over pi times f of r w over 1 minus z w bar squared dw. And you can just do a very easy substitution here, literally like a calc 3 change of variables. Basically, u is rw. I'll stick with w though. So this is going to be equal to 1 over pi r squared. RD here means it means a set of all z whose modulus is less than or equal to r. That's all RD means, which is the same thing as you multiply everything in the unit disk by r. And so if you, yeah, so you're going to get 1 minus zw bar over r. All right, so what I want to do is use dominated convergence theorem. Just by continuity for any fixed z, f of r z as an element in the complex numbers converges to f of z. And if I can get a dominator, I can just use dominated convergence here and just let r go to 1. That's not too hard, but I will just go through the details. In particular, well, yeah, sorry. So let's get a pretty easy bound here. Well, W is, yeah, W is in, Right, so sorry. W is in this here, R time, RD, so that means that the modulus of W is less than R. So this is simply less than modulus Z. So all that means is, let's use triangle inequality. So add and subtract ZW bar over R. So that's going to be less than 1 minus Z W bar over R plus Z. And so that implies the denominator here is going to be bigger or equal to 1 minus modulus Z. And remember, Z is fixed. We're just fixing Z. So this is certainly between 0 and 1. So the whole thing here yeah, this is going to be less than or equal to f of w and modulus over 1 minus z squared. So now, just by Cauchy-Schwarz, we have a dominator basically when you take. Well, yeah, certainly this is my dominator. This is an L1 because just use Cauchy-Schwarz. The L1 norm is less than or equal to the L2 norm if we're integrating over a finite set, basically. Well, not exactly, but and this is basically my dominator. So by dominated convergence theorem, we have f of z is this limit here. R approaches 1 from the left. And I don't feel like writing this whole integral over, but let R go to 1 everywhere. And yeah, we get this is equal to, sorry, don't want absolute values. One over pi times this integral here. So a fairly easy limiting argument. And of course, this is, I probably should have made this clear before, but yeah, this is going to be the following, where kz is simply 1 over 1 minus wz bar squared. So remember, when we do this inner product, we get a complex conjugate. So for the integral, it's going to be z w bar, like right here. And we proved uniqueness. So this is exactly the unique element that basically induces pointwise point evaluation. Okay. Right. So let me connect. Let me connect this to orthogonal projections, and this is very general. So I should mention, for various holomorphic function spaces, you do similar things to prove you know, what the reproducing kernel is. So for the Fock space with alpha equals 1, it's going to be e to the z w bar. I'm using somewhat similar ideas. Yeah. So yeah, let me connect things to the orthogonal projection. So let me prove a lemma. And I should also mention that everything I'm doing is in the book. I'm following the book pretty closely from now on. And this is why I like the book. It has connections to complex analysis. Because the author, Barbara McClure, does complex analysis and functional analysis, so it makes sense. All right, so let's prove the following in general useful lemma, and that'll allow us to connect orthogonal projections to reproducing this function kz. And I should say this function kz is called a reproducing kernel because in some sense it reproduces my entire Hilbert space. You get your function f by inner product and taking an inner product of f with one of these kz's, in the sense that f of z is f inner product kz. All right, so an easy lemma, but still needs proof. So let's say I have a closed subspace of a Hilbert space, and let's say P is the orthogonal projection that we talked about, I think, 2 videos ago. If X and Y are in H, we'll talk more about this later, but we have the following. And the proof is actually, if it wasn't in the book, I'd give it for homework because it's a nice little easy problem. So let's say X is X1 plus X2, and Y is Y1 plus Y2. I think the book uses M and N, not sure why, but so here this is an M, this is an M perp, M perp. Make that a little neater. All we're going to do is compute both sides and see what we get, check that they're the same. So first of all, P of X is Px1 plus Px2. And that is, well, just Px1. Really by definition of what P is. But if you forgot the exact definition, it's fine. You just need to remember that, well, Px1 is x1, and P applied to anything in the orthogonal complement is 0. P is 0 on the orthogonal complement. And similarly, Py is y1. So Pxy is going to be equal to x1, y1 plus y2. Well, just distribute this. X1 inner product y2 is going to be 0. Because remember, this is an M. This is in the orthogonal complement. So this is just going to be x1 inner product y2. And let's check what x inner product Py is. X1 plus x2 inner product y1, but again, This is in y perp x2, and y1 is in m. So x2 inner product y1 is 0. So we get the same thing. This is x1, x2. Sorry, x1, y. Yeah, sorry, this is x1, y1. Sorry about that. x1, y2 inner product is 0. And this is also x1, y1. Sorry about that. So they're equal. Not a whole lot to this. Okay. Right, so let's answer the following question. Well, so certainly L2, A2, the Bergman space, is a closed subspace of L2. So we can ask the question, what is the orthogonal projection from L2 to the Bergman space? We can answer that very easily. Let's say f is an L2. Pf of z is something in A2. So we can apply the reproducing property so I really don't want to write A2s everywhere, so I'm just going to not do that. Well, f is an A2, kz is an A2. So I can certainly apply this lemma here, bring the p over. Well, kz is an A2, p doesn't do anything to stuff an A2. So this is just simply integration against the reproducing kernel. That's exactly what the orthogonal projection is. It's a integral operator. Okay, so let me very briefly talk about in general what a reproducing kernel Hilbert space is. Let's say in general, omega is just some set. Literally could be anything, any kind of set. And in practice, in applications of what I'm going to do to machine learning, this could be literally anything. Could be something from biology related to biogenetics, protein structure. I mean, there literally could be anything. So what is a reproducing kernel Hilbert space? Reproducing kernel Hilbert space. Well, reproducing kernel Hilbert space, by definition, is a Hilbert space. I don't know why my instinct is to write a script H. I'm writing Hilbert space, but anyway. So it's a Hilbert space, script H, of functions in applications to machine learning, usually real valued functions, but whatever, doesn't really matter. let's just say for us, it's complex valued. Okay, so it's a Hilbert space, so it has some inner product that and it's complete. So it's just some Hilbert space of functions where for any z in my set, this is less than or equal to some constant z times the norm of h. For any z in omega and any f in my Hilbert space. Okay, by the Riesz representation theorem, because we have a Hilbert space, there exists some h called the reproducing kernel. So actually, in applications to machine learning, you usually start off with a kernel and then build a Hilbert space that forces your kernel to be a reproducing kernel. But we won't get into that unless people want me to. Okay, so right, so what does that mean? That means f of z is f kz for any z and any f and h. All right. So what have we actually proved if you think about it? Well, we've proved the following. Let's say H is a reproducing kernel. Hilbert space. H is a subspace. So, H is a Hilbert space, so it's a subspace. But let's say it's a subspace of some bigger Hilbert space, H prime. Maybe make it a little clearer. Okay. So as a Hilbert space, it's closed. So we have a closed subspace of H prime. So we have an orthogonal projection from H prime to H. And again, H prime is just a larger Hilbert space. The orthogonal projection from H prime to H is simply given by just F inner product KZ for any F. And now just note, this doesn't reproduce. There's no reproducing. And I should say these two have the same inner products. So they have exactly the same inner product. F is in this larger one, so there's no reproducing property. Yeah, there's no reproducing property, so we can't say this is f of z. Right. So basically, this is just abstracting exactly what I have here. A2 is a closed subspace of a bigger Hilbert space L2. They have the same inner product. Point evaluation doesn't even make sense for L2 functions because two L2 functions are by definition the same if they're equal almost everywhere. We don't even define functions in L2 point-wise. By definition, they're really equivalence classes of equal functions almost everywhere. But it still makes sense to ask what's the orthogonal projection, and it's just F inner product KZ, and maybe to kind of emphasize connection to here, the L2 inner product again is the same thing as the Bergman space inner product definition. So yeah, literally the exact same proof, and I don't even think I could give this for homework because it is literally like the exact same proof up to here. Nothing special whatsoever. Oops, didn't mean to do that. That wasn't looking. But yeah, if you just basically go follow these steps here, nothing special at all about the Bergman space or L2. Everything that I have circled here holds for a general reproducing kernel Hilbert space to prove the following. Okay. Yeah, so hopefully this was interesting. And again, if anyone wants me to discuss the machine learning connections to reproducing kernel Hilbert spaces, I'll be more than happy to. I'm definitely interested in that research-wise. Still things to be done in that area, though, frankly, it's kind of a dying field of research because deep learning has largely superseded using reproducing kernel Hilbert spaces for machine learning, but still used in real life. Still have to know it. You still have to know reproducing kernel Hilbert spaces if you're interested in machine learning and want to do data science. But all right. Anyway, hopefully that was useful. Hopefully you enjoyed that. Next, we're going to talk about orthonormal bases. And all right, so long. Take care. Bye-bye.